Okay, so renal lab values are not different than any other lab values, but there was just a lot getting thrown around in the renal lecture, so I just wanted to review some of the high yield topics here. So BUN and creatinine. So BUN is blood urea nitrogen. It's just basically analogous to the amount of nitrogen product in your blood. Basically, the liver is going to break down polypeptides into ammonia. Well, ammonia is a very toxic compound to the body. So then the liver, through the urea cycle, will change that ammonia into urea, which is less toxic to the body. And so urea is really the one that we can, in a normal person with a functional liver, that's the one that we can actually find because the ammonia levels are going to be really small on somebody with a functional liver. So you hear urea a lot. That's just a nitrogenous compound. And then creatinine is used. That's obviously a breakdown product from metabolism in the muscle. So creatinine is really a complete waste product for the body, so this is a great thing. It's not changed or manipulated in the body, so it's a great product to monitor to assess renal function. One thing that should be noted is that creatinine is synonymous to your muscle mass. So, you know, big time weightlifters, African Americans, people who tend to have more muscle mass will have a higher creatinine level on average. So that's something to keep kind of track of. Even the GFR calculations actually take into account nationality in certain cases to help calculate their GFR properly, because certain individuals with a larger muscle mass will have more creatinine, like men have traditionally higher creatinine levels than women, and then African Americans traditionally have higher creatinine levels than other races, and that's just basically it boils down to the muscle mass. So these ratios, you know, the BUN creatinine ratio is just used to assess kidney function. So another thing here that we want to understand is calcium. So obviously you guys have talked about these, and you will talk about them a little bit more in the electrolyte lecture. But calcium is obviously in the body. It is bound to albumin. So normally calcium is bound to albumin. And when we measure the calcium in the blood, we're actually measuring that bound calcium. So, you know, a high percentage, probably 9 out of 10 of these functional calcium molecules are bound to albumin. So we can just lyse these with our analyzer, and we can find out how much calcium is in the body. The only problem is if somebody has really low albumin, then their calcium is going to be falsely decreased. So in those cases, we need to get an ionized calcium, and this will tell us how much free calcium is in the body that's not bound to albumin, and then we'll have a better idea of exactly the lay of the land as far as their calcium is concerned in the body. Sodium gets used a lot, particularly with renal stuff. Sodium is normally bound to chloride throughout the body, so you can really use sodium chloride interchangeably for sodium. Water also is going to follow sodium physiologically, and so we can always kind of think of those things going in the same direction. Fractional excretion of sodium is this really nasty big, it's not that big, it's tangible calculation, but there's no real reason to you know, drag yourself into that in-depth equation at this time. It's really outside of the scope, but what you do need to know is that less than 1% fractional excretion of sodium is normal, and that is usually synonymous with the percent sodium excretion, which is less than 20 milliequivalents per liter. So if somebody's kind of average, their average normal sodium labs are going to be less than 1% fractional excretion, and then synonymous to that is going to be less than 20 milliequivalents. If it's greater than 40 milliequivalents, then it's going to be like greater than 2% fractional excretion, like we saw there, right? So sodium chloride make up the lion's